And welcome to another fantastically easy lesson since we covered this last year, so this should be another little bit of a review for you. So unit 3.3 is about Q equals mc delta T, that fantastic formula we used last year to calculate the amount of energy that a substance either possesses or also what it can transfer to another substance of lesser temperature, for example. So Q represents the amount of energy transferred based on the mass of the substance, its specific heat, so its ability to store energy, and the change of temperature, the variation of temperature of the substance. Now, in general, Q is calculated in joules, but because very often the amounts will be large, we'll tend to express it in kilojoules. But just know that Q, normally when we use this equation, Q will be measured or calculated in joules. We need to convert after the fact to give an answer in kilojoules. The mass will always be in grams. The specific heat is in joules per gram per degree Celsius. I'll get back to this after. And the temperatures are now in Celsius. So we're done with the gas laws. The gas laws always use temperatures in Kelvin. From now on, all temperatures we're going to be working with will stay in degrees Celsius. And delta T, just to refresh your memory, is always temperature, the final temperature minus the initial temperature. So if we break it down and we look at all the factors, but one at a time, we'll see how they influence the amount of energy that a substance, a body, can either absorb or release. So first we'll start with the mass. So we have an example here. We have two beakers with water in them. We have 1 liter of water versus 2 liters of water. They both start at the same temperature. They're both going to end up at the same temperature. So the question is, which one will be able to store more energy by the end of the process? Well, obviously, if you said the 2-liter container, that's the correct answer. I have twice the amount of matter, therefore I should be able to store twice the amount of energy. That's correct. And that's why they put two sources of energy here to represent the fact that you'll have twice the amount of energy stored in this amount of water versus this one. So twice the amount of matter means you're going to store twice the amount of energy, or you're going to require, it will require twice the amount of energy to raise the temperature to the same level as the one on the left, if they start at the same point and they finish at the same point. So twice the mass, twice the amount of energy that can be stored or that it will need to absorb to increase its temperature to a certain degree. Secondly, we will look at the specific heat. So the specific heat is the amount of energy necessary to increase the temperature of 1 gram of substance by 1 degree Celsius. So let's pretend here that I have two substances, substance A and substance B. They both weigh 1 gram. Now the size of the box represents their specific heat. So substance A has a large specific heat, substance B has a smaller specific heat capacity. So they both weigh 1 gram, and I want to increase their temperature by 1 degree Celsius in both cases. So substance A will need 1, 2, 3, 4 joules to fill up my box, therefore to increase the temperature by 1 degree Celsius. And substance B will need 1 joule to fill up the box, in other words, to increase the temperature by 1 degree Celsius. So again, if I go back to the question, which one will need more energy to increase its temperature by 1 degree? It'll be this one. It needs 4 joules. It has a higher specific heat capacity, which means it requires more energy to increase 1 gram of matter by 1 degree Celsius. Now, the converse is also true. If I need to cool off something, which one will cool off faster? Well, this one, this one, it's cooled off. The other one, I need to remove 4 joules of energy to cool it off. So this one will not only warm up more slowly, but it'll cool off more slowly as well. This one will warm up faster, but also cool off faster. Now, if I were to ask you which one will store the biggest amount of energy, again, obviously, it would be substance A. So substance A takes longer to warm up, takes longer to cool off, but it will store the biggest amount of energy. if I may make a parallel, this could be, for example, let me write it down just to help out the explanation. This could be water, for example. Okay, water has a specific heat of 4.19 grams per joules per gram degree Celsius. Let's pretend this is sand. Sand has a smaller one. I don't know it by heart, but I know it's much smaller. So let's pretend we are comparing an ocean to a desert. We know that in the desert, it's very hot during the day. Why? Because the sand has a very low specific heat capacity, which means it's going to gain energy and therefore its temperature is going to increase much faster than the ocean. Water takes longer to warm up, right? So the ocean will take a long time to warm up. That's why in the spring the water is very cold, and during the summer it gets warmer and warmer and warmer, and during the fall it stays warm because it takes time for the ocean to lose all its heat. So the water stays warm much longer. It takes longer to warm it up, but it retains its heat longer because it has a very high heat capacity. Back to the sand in the desert. So during the day, the sun heats up the sand, and every time I fill up a box, that means the temperature goes up by 1 degree. So I can fill up a lot of boxes. I can increase the heat of the sand very quickly, so it gets very hot. Now at night, what happens? Well, it loses that heat very quickly. So it doesn't stay warm in the desert at night. It gets extremely cold. It could be around the freezing point at night. Why? Again, because the sand and the desert per se, the sand has a very small or low heat capacity. Okay, so that's it for the explanation of the heat capacity. So the greater the specific heat, the longer it will take to increase the temperature, the longer it will take to cool it off as well, and also the more heat can be stored within that substance. You have another example here. Oil will heat up faster than water because the specific heat, again, is very low. But you don't need as much energy to heat it up than to heat up water. This you need to know by heart. So specific heat of water, 4.19 joule per gram degree Celsius. So that's an important number. It's a constant. So in your significant figures, in your calculation, you don't count this as a significant figure because it is a constant. And this we've answered already. So the last point, if we look at these specific heats, now we're going to see how we apply this. We're back basically to this equation, Q is equal to mc delta T. So if we look at the first question, calculate the quantity of thermal energy, this is Q, absorbed by a 5 kilogram block of concrete to raise its temperature from 17.1 to 35.5. So we will write down our equation. So we will write, sorry, I'm just going to get a pen. So let's take red. Okay, so calculate the quantity of thermal energy, so that's Q is equal to the mass. The mass has to be in gram, remember? So 5 kilograms, sorry, becomes 5,000 grams times. The specific heat capacity of concrete is 2.10. If you look on the table on the left, you'll see concrete at 2.10 times delta T, 17.1 to 35.5. So my final is 35.5 minus 17.1. Sorry about the handwriting. I'm trying to take as little space as possible because I'm running out of it. There you go. So final minus initial. So if I solve for this, I should get 1.93 times 10 to the 5 joules. Now again, because this number is fairly large, most often we're going to tend to express the answer in kilojoules, so we will divide this by 1,000 to get 193 kilojoules. It's much easier to express our final answer in this number than in this one. It just, I don't know, makes more sense, look better, it doesn't look as big, etc., etc. Okay, so let's look at the second example. Let's just get rid of this. Okay, the second example, a 1.35 pellet of aluminum foil is heated to 205 degrees Celsius and then removed from the heat. After a few seconds, the pellet has released 176 joules of heat. What is the final temperature? So now you have to watch it. We're looking for the final temperature. So this here, the 205 degrees Celsius, is really the initial temperature. So they took the aluminum foil, they heated it up to 205 degrees Celsius, and then they let it cool off, and they wanted to know what the final temperature was going to be. So even if they warmed it up or they heated it up, they really started with this temperature in the problem. So again, if I go and get a pen and I show you what the equation would look like, I will have, now in this case, they're giving me Q. They're giving me 176 joules. That's the amount of heat released over here. It says it, heat released. Now in this case, because it's released, it will be negative. And you'll see how this impacts your calculation. I have 1.35 grams of aluminum. What's the specific heat of aluminum? Let's go and check. Aluminum is over here, 0.9. So 0.900. I will keep all the zeros because that's going to have an impact on my significant figures. Mind you, this is never mind what I just said, this is a constant, so I shouldn't take that into consideration. The temperature, it starts at 205, but we're looking for the final temperature, so I don't know what my final is, but I know that my initial is 205. And there you go, I would solve for TF. So here, my final temperature would be, my final temperature would be 60.1 degrees Celsius. Now, if you forget to put the negative here, obviously you're not going to get the same final temperature. It would not necessarily make sense. Sometimes you'll get a number that does make sense. You won't realize you made a mistake. But to really represent this reality, the fact that the aluminum lost some heat, it released some heat, you absolutely need to put the negative sign here. So please do not forget about that. It's going to cost you points on an evaluation. So the final answer, 60.1 degrees Celsius. So that's it for QMC Delta T. I'll see you around for 3.4 the next time. Bye.